Good morning, everybody. We are starting today's seminar. Let me uh, welcome all participants. You may bookmark the GC website where we broadcast the seminar. I have a few technical comments before we go to physics. One is that you're requested to keep your microphone and camera turned off when you're not talking, and you may raise your hand when you want to uh, say something. Um Please note that the recordings, if they are made, will be available on Indico website, and there is a program of the seminar. The schedule of future seminars is also included. And if you have any technical questions, you may also ask them to me or Gianni Salme. And there is a list of frequently asked questions put on the uh, Indico website. Uh, Coming to physics, let me also mention before we start that next week we will have a seminar by Philip Mannheim on comparison of the light front and instant time uh, dynamics. While today,
Stefan, I think it's in 2 weeks.
yeah, it is actually yes, sometimes I need to be corrected. Please do it without hesitation. However, I hear somebody's microphone uh, uh, working. All right, thank you. So today we will have a pleasure to listen to Carlson, who will be talking about proton radius puzzle. Uh, Carl is known for extensive work on scattering of leptons on hadrons. He was publishing papers on electron proton scattering, on polarization transfer in electron deuteron and scattering. He worked on quark distribution in nuclei. Uh, his expertise extends over a broad range of phenomena that are of main interest to us. Long ago, he worked on bag model, and the scope of his interest can be illustrated by the fact that he was also working on large number of Callas limit for QCD. Today is he can also include in his collection of work heavy quarks and holography. So he is very up to date, contributing to the physics of our interest. And today he will talk about the proton radius puzzle. Carl, can you take over? Hello, Carl. You have to unmute your mic and unmute your camera, or turn on your camera and start talking. Carl? Hello? It looks like Carl is not broadcasting at all.
There's one window which says CC.
Yeah, I clicked on it. Hello, Carl, can you hear me? Carl, if you can't speak, please write a message. Type a message in the chat area. It's in the left-hand lower corner of your screen if you're on Jitsi. Oh, I see. Carl is saying he cannot turn on mic or video. Error obtaining permission. But perhaps you have some other application that uses your microphone and camera. Carl, can you see the chat? There's advice by John. Maybe you can leave the meeting and get on it. Carl, if you can hear me, try to go on Jitsi to settings and see your microphone settings.
Now, I gather I can hear myself. Can you hear me?
Oh yeah, hello, Carl. How are you?
Oh,
I'm so
I'm
happy you
wonderful.
connected finally.
I'm happy I'm connected also. I'm on Safari now. I was on Chrome. I don't know what the problem with Chrome was, but here I am.
All right, so let's start without delay, and you're
I'm
very welcome. Please, the floor is yours.
okay. Thank you. I'm quitting Chrome just to keep the echo down for myself, and I'm now looking for the share screen button, which I had found before. Yes, uh, and it says allow to share the screen. Let us see what happens here. Can anybody see my screen? I do not see my own screen.
It disappeared for a moment.
Aha.
You may share an application instead of the screen, because if you share the screen, we see other stuff behind your slides.
Okay. I can, let me see here. I can go to enter full screen. And the question now is, what do you all see? Do you see
It's
my screen?
okay. It's quite visible, and you don't need to do more or better.
Mm-hmm. Okay. Shall I start then?
Yeah, please go on.
Finally. Okay, wonderful. Thank you for being here. I'm sorry for all the difficulty getting started. Uh, I am glad that the International Light Cone Advisory Committee is doing these seminars. It's hard on all of us not to be able to meet in person. I miss you all. I see small pictures and names of friends that I haven't seen for a long time. I would like to see you again. But in the meanwhile, as I say, I'm glad that the ILCAC is doing this, and we shall proceed. I'm going to talk about a proton radius puzzle update. This is not precisely a seminar per se. This is a report of what goes on. I will talk later about work that I have done myself, or at least mention some of it. But I would like to tell you what is happening in this field of the proton radius puzzle. And what I'm going to do, in case people start wondering what's happening in this field, is I'm going to show the newest results close to the beginning of this talk, so you have an idea of what's happening. And then I will proceed and talk about a bit of history about how we measure the proton radius, talk about modern times and scattering data, talk a little bit about the reanalysis of the data, talk a little bit about deuteron measurements, and talk about the actually important subject of two-photon exchange corrections. The uncertainties in these corrections may or may not be a bar to improvements in the proton and other light nuclei measurements in the future. And then I will close. So let me ask if anybody can speak, if you are still seeing me or seeing the screen, that is to say, and hearing me well.
I hear you well.
Okay, that is good. So at least one person hears me well. I will assume everybody else hears me well then also. Okay, I'm about to show some results, but let me say first, the proton radius has been measured in a number of different ways. It's been measured by electron-proton elastic scattering. It's been measured looking at level splittings in ordinary hydrogen, which means electronic hydrogen. The proton size has a small effect on those level splittings, and that can be measured. And most interestingly, in the past 10 years, we can look at the level splittings in muonic hydrogen and get the proton radius from that means also. Now, before 2016, there was a great problem in the sense that the old measurements, the electronic measurements, whether you did atomic physics or scattering, were giving one value, about 0.87 Fermis, 0.88 Fermis, represented in this plot by this light green band in the right-hand half of the plot. And then along came the muon Lamb shift measurements. I will tell you a little bit about how they were done. And they gave a different value. And the value was down here at about 0.84 Fermis. And the width of this dark green line, I worked on this carefully. The width of that dark green line is, in fact, the width of the uncertainty of that measurement. So that's a very precise measurement. And as you see, they are quite different. They're about 6 standard deviations apart. This is the situation as we knew it in 2016. And then starting in the middle of 2016 and proceeding, there have been a number of new experimental results. And this gives you, I think, all the new experimental results that have been actually published or talked about in conferences to date. And the coding here is that the red, including this pink, which I can call light red, are atomic physics measurements. And down in the bottom, the blue, are electron scattering measurements. And the abbreviations are Max Planck Quantum Institute, year 2017, or reported in 2016, but published in 2017. LKB is the Laboratoire Kostler-Brassel in Paris. York is York University. Eric Hessel's in his group there. There are two more MPQs down here. These two MPQs should be taken together because these two MPQs are basically the same group, the same apparatus, but you can keep them separate from the first MPQ, which is a different group at the opposite end of a rather long corridor in the MPQ building. Different principal investigators, some overlap in the totality of the group. So and different methods, I think I said that. And so there are 5 measurements, if you count these 2 at the bottom, which have not been published and have not been pre-printed, but have been reported in public conferences that I've been present at. There are then 4 or 5 measurements, depending on how you count the last 2, of which 4/5 agree with the muon Lamb-shift value. These 5 measurements are all electron atom measurements, ordinary hydrogen measurements. The LKB agrees with the old electron value, but 4 out of 5 agree with the muon value. And then further down below are new scattering experiments. The first of the 2 is the PRAD experiment from JLab, which first reported a result in 2018 and published in 2019 at about, at a value that agreed again with the muon value. And this ISR is the initial state radiation experiment at Mainz, which has a large error bar so far. They plan to run another experiment which will reduce the error bar. They know what they're doing in detail now, and we shall see how that goes. But they are compatible with the larger value, but with the error bar, you can also say they are pretty much compatible with the lower value also. That is where things sit today in terms of data that's available, and it makes it look like the lower values are doing better. Here are some references. You can look at that later if you're sufficiently interested. You can either get the recording or download my slides. So all of a sudden, we can make a summary. You can make your own summary. But CODATA, which is the Committee on Data for Science and Technology, for those who don't know it, it's a very useful group of people who keep track of all data that's available and does averaging in suitable ways for lots of important quantities. And CODATA 2018 means CODATA based on data available through the last day of the year 2018, which means it can't possibly itself be available in 2018, but was available by the middle of 2019. And they finally have given up. And this is the way one ought to present the previous slide today. The CODATA value now incorporates the muon Lamb-shift value. And if this is all you ever see, you would not say there was a proton radius puzzle today. Nonetheless, I have a talk, and I will continue, since you're interested, I'm sure, in how some of those measurements were made and what a theoretical physicist might do to help out the situation. First, let me say something about electron scattering. It's one way to measure the radius. How do you measure the radius? Well, everybody knows that if we're dealing with a spin-a-half target, there are 2 form factors, one for the electric charge, one for the magnetic charge distribution. And there's a cross-section, which is given by the sum of the squares of the electric and the magnetic form factors. With this tau over E factor, tau is the momentum transfer squared given in a dimensionless way. And 1 over epsilon, or epsilon, is the ratio of the longitudinal to transverse polarization of the photon that's being transferred. It's a virtual photon, so it can have a longitudinal polarization. And it can be worked out in terms of the scattering angle. So it's given there. So there are 2 terms there with any reasonable range of kinematics in your experiment. You can separate those 2 quantities. If you're at very low q squared because of that tau factor, you're mainly measuring the electric form factor. And you can define the charge radius for historical reasons as a derivative of that form factor, or minus 6 times the derivative of that form factor at q squared of 0. So there is the charge radius as defined. And real data doesn't make measurements at q squared of 0. It makes measurements at q squared close to 0. And so you've got to get the slope close to 0 and then extrapolate into q squared of 0. And a lot of the data well, it began certainly in the middle of the last century, but the best of the data is all from the 21st century, and the biggest and best data set came from Mainz in the year 2010. Still the biggest and best data set came from Mainz, was reported in the PhysRev letters about 10 years ago. Has a relatively low Q squared range, although not as low as we'll see later, but 0.004 Jev squared is the end of their range. And they their own analysis of the data gave them a proton radius of what I'll call 0.88 Fermis to about 1%. So that was it. I have some pictures there. Mainz, you probably know, is the city of Johannes Gutenberg, so they're very famous for that. They're also the city of this lovely electron accelerator that we call MAMI, and there's a picture of one of the spectrometers at MAMI. Excuse me. And nowadays, if you've been reading the newspapers, there is a company called BioNTech, which is the German company that may have a COVID vaccine that's 90% effective, and they are also located in Mainz. So Mainz is going to become perhaps more famous. We shall hope that vaccine works nicely. And then we can talk about making measurements from atomic energy splitting. Here is a nice formula. The energy splitting between a couple of levels, one of which is the S state, has a term, or this is our atomic energy level, has a term that's just due to QED. If you are sufficiently, what is the right word? If you have a sufficient stamina, you can calculate that QED correction to quite a large amount of accuracy. And then on top of that, particularly for S states, there's a proton charge radius term. This next term is something you can actually give as a homework problem for a junior level using American language, a junior level college quantum mechanics course, and your students will be able to work this out after you've begun the quantum. And then there are 2 photon exchange corrections, and then there's some very small corrections that I won't talk about further. These 2 photon exchange corrections have been calculated. They're important. I'm going to talk about them more later. And what you need, though, to make this whole thing work is, to start with, you've got to get this first term very accurately. I said that requires stamina, and it does. This is a diagram. This is just in case. I once went someplace, and a very distinguished physicist asked me, what's the hyperfine splitting? Everybody knows. Well, no, this is the level diagram, not the scale. But there's the level 1, level 2, level 3, and the hydrogen atom. We all know that to a first approximation, level 1 is what it is. Level 2 has S states and P states. They're all degenerate. Level 3 has S, P, and D states. They're all degenerate. If you add in the fine structure, you get a bit of splitting between the 2p½ and 2p3½ state. It happens that if you solve the Dirac equation, that's one way of getting the fine structure. The 2s½ and the 2p½ are still degenerate. If you start doing quantum electrodynamics and take into account the possibility of closed loop corrections and so on, there's going to be a small level splitting between the 2s½ and 2p½ state. That little level splitting is called the Lamb shift. That can be measured. It's a rather small splitting. The splitting between the 1s state and the 2p state, or the 1s state and 2s state, is a rather large level splitting. So there are big level splittings here and small level splittings here. And the hyperfine splitting is due to the electron spin, proton spin interaction. It is even smaller than the Lamb shift and smaller than the fine structure for hydrogen. But there's the level splitting. I'll be talking about that. But if you want to do the calculation in QED, you have a bunch of terms. And you can say, what is the lowest level formula? You probably remember either from taking the junior level quantum course or from teaching the quantum course, that in some units, the lowest splitting in the hydrogen atom is a half mR squared. It's the binding energy of the 1s state, at least. And then if you want to do a more complete calculation, you have an expansion that you can organize in terms of a 1 plus ... plus order alpha cubed over 2 pi, and order alpha over 2 pi to the 4th power, etc. And if you're interested in knowing how far you have to go in order to do an accurate measurement of the proton size, you've got to subtract out the QED term from the experimental value, and what's left is mostly due to the proton size. Did you ask yourself, how big is the proton size? Oh, from the previous formula, I've written it down here again. You have something which is about a few times 10 to the minus 11 times the main term. This main term is called the Rydberg energy, or the Rydberg. But you have a few times 10 to the minus 11 times the main term for the state that you're interested in, which is n equals 2, and for Re about 1 Fermi. You look at this number and you look at the numbers above and you say, if I have done the 3rd order calculations and nothing more, I haven't gone far enough. I've got to do the 4th order calculations in bound state perturbation theory. This is a lot of work. The experimenters had gotten the necessary accuracy already in the early 1990s, and so it was up to the theorists to catch up. And finally, in or about the year 2000, these 4th order terms became available, and measuring the proton radius from atomic physics became possible. This is an old version of a plot that I showed earlier. This is data from all of which was from before 2016, from the splittings in atomic physics, where you have some labeling here on the left-hand side of which splittings were in use. The first 3 measurements are from the actual Lamb shift. Then this 4th one down is from the 2s, 4s splitting. You need a little bit of extra information. You take the 1s, 2s splitting to add to it. But you have here a bunch of measurements, none of which are a 1% measurement. The best might be a 2% measurement. And you got your small experimental uncertainty by taking the 15 measurements you see there and averaging them suitably, hoping there were no correlations. But everybody want to say, I want one experiment that's going to give me 1%. And that's what we have today. So this is the old stuff. It's reasonably consistent, and it gives you this 0.88 Fermi radius. Somebody will, or they should, ask if the new measurements are giving 0.84 Fermis down here. It overlaps a little bit with these, but basically much smaller error bars. What's wrong with all these measurements? I have no idea. As far as I can tell, neither does anyone else.
Carl, can I ask
yes,
a general
sure.
question?
Mm-hmm.
For the scattering, you define the radius as the derivative of the form factor.
I did, yes.
What's the definition of the radius for the atomic? Isn't it the matrix element of R squared? The ground state?
Yes, I'm going to come to that. There was, when we were still only doing non-relativistic physics, we got the RMS radius by doing just what you say. You take R squared, you multiply by the wave function squared, you integrate. You get the RMS radius squared. That was the definition. You can prove that that's equivalent to the definition I showed you non-relativistically. Relativistically, you're a little bit up in the air, and so what used to be a result has turned into a definition. And then you're asking the question now about atomic physics. I will get back to that because that's an important question. Okay. You have to do a calculation. This is roughly the beginning of the answer. You have to do a calculation. You have to realize that the proton has got an electric and a magnetic form factor, and you have to, in an atomic context, calculate how the proton size and how the magnetic and electric terms are contributing to what you're going to see. I will come back to that. It's actually a crucial question.
I would like to, I would like to ask, you didn't list in QED correction that would involve logarithm of alpha. What was the reason?
Oh, I just left them out. I'm sorry. I'm just the alpha cubed log alpha, alpha fourth log alpha. I'm sorry. They are not omitted in the calculation. Okay. They're just omitted from my writing. Yeah, yeah. In fact, I think that was Phil Mannheim who asked this question. Here is the answer to his question: why in atomic physics do we use the derivative of GE and not something else? Philip had one example of something we could have used. Another thing we could have used is to take the derivative of the Dirac form factor F1 instead of the derivative of the electric form factor GE. And the answer, well, I'm not going to show you the calculation, but the answer is you have to do a relativistic perturbation theory calculation to get the proton size effect on the atoms, and you discover it's proportional to a derivative of F1 plus a contribution from F2, and you put it together, and my gosh, it is precisely a derivative of GE at q squared of 0. And so that's why we do this. I might make another remark about this slide, which is who is really the target of the slide? Is it Phil Mannheim or is it somebody else? And the real target actually is somebody else. There are lattice gauge theory calculations of the proton radius nowadays, which are very nice. And they, for reasons not known to me, give you the derivative of F1 as the chosen proton radius and then make corrections. And they actually take the data and correct it to give you the derivative of F1. I find this a little bit funny because our friends in atomic physics don't get a choice. We who are in nuclear particle physics and do scattering can choose between F1, F2, GE, GM. The atomic people don't get a choice. They get what they get. And I think it's in our interest just to match them so we all talk about the same thing naturally. In any case, go on. What happened with...
This Dombrowski, maybe one of the confusions is that really GE prime is just the light front definition from, for the Drell-Yan-West formula and so on. And the lattice is always doing instant form. So maybe there's a confusion about how you define the actual radius, because if you just use light front, of course, you get the physical radius at fixed light front time is given correctly by GE prime.
Yeah, I would hate to get involved in a discussion between you and Jerry Miller, where Jerry managed to prove that, in a light front, what you see naturally is a projection onto a two-dimensional plane, and F1 comes out more easily than GE. You've seen that discussion.
Yeah, sure, but there is a difference between instant form and front form. That's all.
There is indeed. But the atomic people, the calculation, once you sit down to do it, is pretty elementary of what you see in atomic physics. You don't get a choice. Okay. You see GE.
Right.
Yeah. Right. Let me talk then a little bit about muonic atoms, which came about in 2010. People have been thinking about it for about 40 years as of the year 2010, when the Paul Scherrer Institute was first proposed, not built, but proposed under a different name back then. One of the things on the list of experiments that they could do was to measure the proton charge radius using muonic atoms. So this goes back to about 1970, but it really got going in about the year 2000 when the apparatus started to be built, and it came to fruition in 2009 in terms of the result, in 2010 in terms of the publication and announcement date. What was the great attraction? The great attraction had to do with the fact that muons weigh about 200 times what the electron weighs. They therefore orbit about 200 times closer to the proton. In terms of angular size, the proton looks 200 times bigger. The effects of the proton size are magnified. And despite the fact that you have a short muon lifetime, you had a real opportunity to get a more accurate proton radius because the effect on the level splittings was going to be so much greater. And this was done finally by the CREMA collaboration. On my better days, I can remember what CREMA stands for. Charge Radius Experiment with Muonic Atoms is what it stands for. And they looked specifically at the Lamb shift, which was the 2s½ and 2p splitting, and they got shock, a number which was basically what you see there. The number you see there, 0.840 or 0.84 to two figures, is the 2013 reanalysis of their original data, but their original number was very close to that one, and definitely 0.84 Fermis and not 0.88 Fermis. And so there was a conflict. There's a repeat of the number, and there was a little table that showed you the electron number, 0.88 Fermis to 2 figures, the scattering number, 0.88 Fermis to 2 figures, and the muon number, 0.84 Fermis to 2 figures. And the muon scattering, there is no, strictly speaking, this phrase, no data yet, is not true. There is data on muon proton elastic scattering going back to the 1960s, but none of it is at the moment sufficiently accurate to be of interest, but we hope that will change soon. Let me say a little bit about modern times and scattering data. I just said we have a hope that muon proton scattering data is going to soon be more accurate, accurate enough to get a radius measurement out of it. And we're all looking forward to the coming data from MUSE, which is the muon scattering experiment. That's at the PSI in Switzerland. And it will do both muon proton and electron proton scattering at a Q-squared, which is about half of the Mainz experiment. And the electron, rather the radius gotten from electron scattering and the radius gotten from muon scattering by themselves will be accurate to about 2%. But, interestingly enough, the relative error between the electron and muon results should be about 0.7%, and so that should be quite interesting. There was serious hope that we would know the number by now, but we do not. And the people running the experiment complain about the COVID virus like the rest of us. They are not running, in actual fact, because of COVID. So we are still awaiting results.
Carl, can I ask, it's Philip again, can I ask a separate question?
Sure. Sure.
The scattering get down to, you said to 0.004 and now they're trying 0.002.
Yes.
How much would they have to be off in order to get you down to a radius of 0.84 Fermi? I mean, it's not just the last little inch.
No.
I mean, it would look like the data would be completely, you have to have a huge, like, I don't know, 5% change. Do you have any sense of how big it would have to be?
Stan Gwazi, I think Carl got off the line, so we have to wait.
Stanislaw, I'm sorry I got your name wrong earlier.
Don't worry about it.
That's okay.
So, can you hear me again?
I can hear you, yes. Thank
Okay,
you
was I
for coming
offline?
back.
Yeah, I don't know what happened. I went back and looked at my, what is it called, Jitsi screen, and it said I was both muted and I had my camera off. I don't know what happened, since I didn't consciously turn my camera off or mute myself. But in any case,
I didn't do it.
You didn't do it either. Okay, but I can hear you and you can hear me then, apparently. Okay.
Right. I turn off my mic and you should continue.
Okay. In any case, I hope I made these comments when people could hear it. And there are 7 more experiments. One at Sendai in Japan with a low energy electron accelerator, which is very good for low Q-squared experiments.
Carl,
Yes.
You're not broadcasting your slide.
Uh-oh. Uh-oh. Let me try this again then.
Now I see your face.
Well.
Now I see your screen.
Okay. And do you still see my screen?
Yeah.
That's good.
This is already good enough.
Okay, much better than my face. Okay, good.
No, I didn't mean that.
That's all right. Don't worry.
Carl, we got cut off a moment ago. This is Philip again. When these experiments that are pushing down to 0.002, I mean, it's sort of a hidden assumption that the extrapolation is going to go haywire right at the end. But if it's a smooth extrapolation, how much would the data have to be changed before you come right into Q equals 0 in order to get down to 0.84 Fermi? It would seem like an awfully big change. Oh. I guess I'll never get an answer.
Philip's Jitsi connection takes over the floor, and Carl is cut off by it.
So, hi, can you hear me again?
Yes, I can hear you. I don't see yet your slide.
You don't see my slide. Okay, that's not so good.
Now I see your face.
You see my face? Okay. And do you see my slide?
No.
You don't. Oh dear.
Philip Mannheim is competing with you for the screen.
Apparently so. How are we doing now?
I see now it's okay.
Now it's okay. I enjoy Philip's.
Philip, perhaps you should say what you wanted to say without turning on your camera. Maybe that will solve the problem. Or...
Yeah.
Philip is not saying anything. Please, Carl, please continue.
Okay. Maybe we have to put a moratorium on Philip so he doesn't take over my screen. But that would be sad. I'm sorry. I would miss him. In any case, there are 7 experiments. I will just skip reading the rest there. And I had 3 other topics to discuss, and let me see if I could discuss them briefly. One of them is a discussion of fitting the old data. There is a question of why the proton radius is big for some people and small for other people. Why does PRAD get one answer? Why does MINDS in the old days get another answer? And some of it may have to do with the way the data is analyzed. PRAD only has a limited range of Q squared. MINDS has a much bigger range of Q squared, and one can start looking at this a little bit in more detail. And quite a number of people have done so. And I have here what by now is a rather old slide, but this is a seminar announcement from Doug Higginbottom, and you can read the title, or if you can't, I will read it to you. The title is Why the Proton Radius is Smaller in Virginia. It's not only in Virginia that the proton radius is sometimes bigger and sometimes smaller. Here is a partial list of contributors. I'm on here under the name of Griffioen et al., but there are lots of other people on here who've done interesting sorts of work. And the basic viewpoint, I think, that can lead to small results is that the charge radius requires an extrapolation. There are lots of parameters. If you have too many parameters and you have lots of data outside the low Q squared region, a lot of the data at high Q squared is going to affect what happens to the extrapolation down to Q squared of 0 and maybe throw you off. If you have fewer parameters and less wiggly functions, or if you limit the data just to the lowest Q-squared data points, you get a rather different result. And this is a simple plot. If you look at it, this is all the Mainz data that's at a Q-squared below 0.02 Jev squared, or roughly the pion mass squared. There are 209 data points there. If you had a little bit more time, you could count them up. But you can fit that slope. You can even fit a slope and a curvature. But the slope is going to be something that corresponds to 0.84 Fermis, to about 1%. I find that remarkable. And going along with this is the data from PRAD. And this is these are two plots directly from PRAD, from the experimenters there, showing their data in red and mostly Mainz data in black. And there are two plots, and the difference between them is on the horizontal axis. The left-hand plot has a wide range of Q-squared compared to the right-hand plot, which matches what I showed you before, 0 to 0.02 Jev squared. If you look at the right-hand plot and you look at the red points and the black points, I think by eyeball, at least you would say, they agree with each other. Okay, they agree with each other. If you look at the left-hand plot, you can see the red data point sticking up above the Mainz data at Q-squared above pion mass squared, 0.02 Jev squared. And so there's a data disagreement at the higher Q-squared. And if you just look at the right-hand plot, you say, well, what is PRAD doing? Well, most of the PRAD's data points are at low Q-squared. They are basically getting their answer from the right-hand plot. And his Mainz got a smaller answer if they only took that set of data. PRAD gets a smaller answer also. And there you see basically 0.84 Fermis is the proton radius coming from PRAD. Anyway, it's still unsettled. If you want to amuse yourself, you can look up this paper, Avoiding Common Pitfalls and Misconceptions and Extractions of the Proton Radius. It is not published by me. It is one of the few times that I have been the subject of a paper rather than the author of a paper. I'm not the only subject of this paper, but if you wish, you can take a look at that. In any case, the possibility of a large proton radius, I probably don't need to say, but I will anyway, is truly exciting, because if the larger radius is correct, then you have a breakdown of electron muon universality, and you're on to the business of physics beyond the standard model. If the difference is robust, you should be really happy. All of us should be really happy. A little bit of a mop-up here. Stanley will tell me when I should quit, I hope. But in any case, let me talk a little bit about deuteron measurements, because it's relevant. The 1s to 2s splitting can be measured to phenomenal accuracy. Why can that be measured to phenomenal accuracy? Well, there are two reasons. One is that the 2s state is metastable. Metastable means that it is almost stable. It lives a long time. Quantum mechanically long-lived states are very narrow, have very well-defined energies, and so you don't have any fuzziness as to where the state actually is lying. One of the big difficulties in atomic physics is finding out just where the state is lying, because there's a bit of a spread in the energy of the state for quantum mechanical reasons that we will understand. Not so for the 2s state. It's got zero width on the relevant scale. And so now it becomes a question of how well you can do the calculations, and you can't do everything very well, but the things that contribute to the difference in the proton radius and the deuteron radius can be calculated very well. And you take the difference in your 1s to 2s splittings for these two cases, and you can turn it into a number for the difference between the proton and the deuteron radius, or more precisely between those radii squared, and you get a number that's phenomenally accurate. You see, it's the difference is about 3.8 Fermi squared, but the error is down, far down. So it's, and let me ask, can you, I have this cyberspace voice telling me that live streaming is on. Can you see my slide?
Yes, we can.
Oh, excellent. Okay. This means that if you can make measurements on the deuteron, you basically have measurements on the proton. And merely as a reminder, I show you the slide that I showed you before. And look at these two pink points, MPQ 2018. One has a letter D. that letter D means that measurement is actually not on a proton. That measurement is on a deuteron. And somebody took the isotope shift and just moved it onto this graph. It's an independent measurement from the other one. It's not an independent group, as I said before, but it's another measurement. You can run this backwards, by the way, because what you saw just above was an electron measurement. You can do the same thing for the muon measurement. This has been done by Crema, and you discover, the deuteron radius you get by measuring the deuteron directly, and the deuteron radius you get by measuring the proton and then using the isotope shift is not quite the same, and they differ by 2.6 standard deviations. There's a plot down there, and the 2 points you're looking at are the 2 top points of the 5 that you see in this little plot at the bottom. There is a difference between the Lamb shift on a proton and the isotope shift and the Lamb shift directly on the deuteron. So 2.6 sigma. So the question you see over there on the right, are you worried about 2.6 sigma? Maybe not, but there's a little bit of a problem there. The last thing I'm going to discuss, again, I'm conscious that I've been running a little bit farther than I should, although it was a little bit late getting started. But I can stop at any time, but I will continue until I'm stopped, which is that I would like to say something about the 2-photon exchange corrections. And if you're doing this for a proton, you're doing a dispersive calculation. If you do it for helium-3 or something else, you still can do a dispersive calculations. What that means is the following. The 2-photon exchange relativistically is a box diagram with 2 photons going across. There you see it for a muon and helium-3 in this example. And the one way to do the calculation is to put the 2 intermediate fermions or 2 intermediate non-photon states on shell. If you do that, you will get the imaginary part of the diagram. That's something that you can prove. The imaginary part of the diagram with these guys on shell means that the left-hand part of the diagram is a muon or electron, something or other scattering. And the right-hand side is this complex conjugate. And so this thing is a cross-section. The imaginary part of this thing is a cross-section for a muon whatever or electron whatever scattering. And so you can get that from experimental scattering data. This is wonderful. And since what really only matters for this calculation in practice, since you know what to do with the upper line, you can use electron scattering data, whether you're doing muonic atoms or electronic atoms. And mainly what you need is low energy data. And once you've got the imaginary part, you can use the magic of the Cauchy integral formula to reconstruct the whole diagram. That's the subject of dispersion relations. And there's a bit of a problem in that one of the amplitudes requires a subtraction. I won't maybe say too much about what that is, but there's a term that is not experimentally measured and you have to estimate somehow. So you start with a proton. Okay, for the proton, not so bad. You see over here the QED term. This is the theoretical calculation. The QED term is something. The proton radius term is something. And the 2-photon exchange correction is something. The units here are all MeVs and Fermis. The number that's mostly used, is not the only one available, comes from Bierce and McGovern. And you have faith that your theoretical calculation is good. And so the experimental number is something or other. The theoretical number is up there for the QED, etc. And so you solve. And this is where the number that the experimenters give you is coming from. If the 2-photon exchange corrections for the proton were perfect, the experimental uncertainty would not change by that much, or the uncertainty you get in RP would not change by that much. So the theoretical uncertainty is quite noticeable, but not dominant. So you could do better, but the theory is okay for the time being. And I would like to jump to a couple of other things, which is to say, we could be interested in scattering off deuterons, helium-3, helium-4, for similar reasons. You would like to find a radius discrepancy, if there be one. And something that you need to start with is the...
Can I just, Stan Browski, can I just interrupt?
Hi, sure.
Is that when you do this dispersion calculation, I understand the imaginary part, but the real part involves the local 2-photon interaction on the quarks, which is called the zero fixed pole problem.
Yes.
And it's really true that that you can actually deal with that. I mean, there is ambiguities and controversy about how you deal with the local two-photon interactions on the quarks.
Yeah, I think it's not a problem. It's sort of on my list as it's straightening this out with you someday, since I've heard you say this before, and I think it's not a problem, but you keep worrying about it.
I do.
Yeah. We should settle it down, Stanley. That's what I'll say for now. We should settle it down. I think it's not a problem. I think it's there. It has to be there.
Okay.
And what's done already. But
Carl, at the risk of you losing a connection, Philip again, can I ask another question?
Go ahead.
Don't you need the cross graph of the two photons for gauge invariance?
Yes. Can you hear me?
Yes.
Okay, good. The answer is absolutely yes, of course. But you've got a blob there. And so what goes on inside that blob? Well, you may cross inside that blob the bottom connections of the photons. And so the cross graph is there. It's hidden by that blob. If I were doing the elastic calculation, I could put in, for example, just a proton or a helium-3. And if I put in something more explicit in the intermediate state, I'd have to show you the cross graph. But if I show you just the blob, it's there without my having to show it to you explicitly.
And you're saying that the imaginary part can be calculated without including the cross graph explicitly? Without cutting.
Yes. Yeah, this you can do. This you can check up yourself. Yes, you can actually do the explicit calculation for the electron-proton case, two-photon exchange, etc. The cross graph doesn't contribute an imaginary part.
Oh, okay.
But has to be included if you want to get the whole correct answer, of course. But it doesn't contribute to the imaginary part.
Well, then the construction of the real part is not reliable by the Cauchy integral.
No, you've got to get it back because the imaginary part will satisfy gauge invariance by itself from the one diagram.
Yeah, no.
If the guy goes off shell, yeah, you get it back. You get it back.
Okay.
Everything is there. This is maybe more of an answer that you want, but if you do the so-called Born calculation, which is the diagram you're looking at now, you can imagine an elementary helium-3. It's probably better to think of a proton. You have a proton going across. You can do that diagram in terms of F1 and F2 and work the whole darn thing out. And you can, without doing any tricks, calculate the energy contribution from this diagram. And then you can proceed using dispersion relations to mimic what you have to do in the more general case and show that you get just the same answer. So in one case, you're just using the imaginary part that came from the uncrossed graph. And the other case, you don't get the right answer unless you have both terms in there. You nonetheless end up with the same answer. I can show it to you someday when we meet.
Hey, Carl, how long would you like to talk from this point?
I can quit at this point. Should I
tell you about... I didn't mean to quit, but...
Yeah, I'm just going to make a few comments about helium-4 and then stop, basically. So if I say 5 minutes,
right?
Be okay.
Yeah, all right.
Good. I'll just go. I was saying we might be interested in helium-4 for similar reasons. We already have a measurement of the radius of the helium-4 nucleus from electron scattering. It's accurate to about 0.25%, as you see it there. And if you calculate what this size contributes to the energy shift in the muonic atom, you can do that, but what I quote down here is what the uncertainty contributes to the uncertainty in your calculation. It's 1.42 milli-electron volts. So that's your target number. You got to beat that number. If you can't beat that number, you haven't done anything useful in a muonic helium-4 measurement of the radius. You've got to beat that number. And one of the crucial things that you need to beat that number is a calculation of the two-photon exchange corrections. If you're doing helium-4, you can do the calculation the way I said, using dispersion theory, or you can do it using a nuclear potential model. You say the helium-4 is 2 neutrons, 2 protons, etc., 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 and you proceed from there, and people have, and you get an answer. And you see there the two answers. And what matters is not the numbers, if the numbers agree. What matters is the difference between those numbers. We're still having a little bit of discussion about what our uncertainty limit should be, as you may see the XX there. But the difference between those numbers is about 3 MeV. And so taking split the difference overall error, it's about 1.5 MeV, which is a little sad because we have not beaten the number that we have to beat. And here is a quote from Randy Pohl, who's one of the experimenters who works on these things. "You are killing our experiment." Okay, I am sorry. But there is hope for the future in the sense that one of the difficulties with the dispersive treatment is a sparsity of data in some of the crucial regions. And one thing you can think about doing to make some of these things agree better is to do a hybrid treatment, which is to use the data where possible and to use the nuclear physics type calculations to fill in the data where the data is scarce. And this has been implemented rather recently. This is October this year preprint from a bunch of people, not including me, but including some of my former collaborators and future collaborators, I hope. And it's been very successful in that you can check up and discover that although they've only implemented it for deuterium so far, they have gotten error limits which are about 2/3 of the previous best. Previous best in this case were the nuclear physics or mainline nuclear physics numbers, and they are beating those numbers. In any case, that is the end of what I wanted to say. I perhaps will read some of this. Because it's remarkable that after 9 years, I'm counting as last year when I think this was true, the puzzle is showing signs of being settled. I have been interested in the fact that for 10 years, there's been very little discussion of the correctness of the muonic hydrogen Lamshift data. This is remarkable, or maybe not so remarkable. Those who know a little bit know that experiment was very hard to make work, very, very hard to make work. But once you've got it working, the analysis of the experiment is easy. As I sometimes phrase it, it's so easy that even a theorist could do it. Nobody doubts that they've gotten the numbers they say they've gotten. The radius results are currently mixed. There's more data coming. To get down to the bottom, either the puzzle isn't a puzzle anymore, or maybe the people who are sticking with the large electron radius from scattering are right. I don't think they are at this point, but I would find that fascinating. Believers in that scenario have to be all in on the beyond the standard model explanation of the puzzle. And so I'll quit with that. I had here, for us who are still in the field, a little bit of mopping up that we can do, but that is what I wanted to say. So I thank you all for your attention. I apologize for the difficulties that we had in getting this thing off the ground. Thank you.
Thank you, Carl. Don't worry about the difficulties. These technical issues are plaguing us all the time. I'm at fault sometimes too.
Maybe not.
So the seminar is open to discussion. Philip, you may come back with if it wasn't clarified what the answer was.
Okay, Carl, you seem to have said the following, which is news to me, and I'd be happy if it's correct. If I just look in ordinary electrodynamics, just electron-electron scattering, no issue with protons and radii.
Sure. Let's even do electron muon scattering to make it look more like electrons and protons.
Okay, and I do the 2-photon exchange, the box graph.
Yep.
Now, we agree that that's not gauge invariant.
We do.
But if I look at the scattering amplitude as a function of the incoming energy, there's a branch cut. Are you saying that the discontinuity across that branch cut is gauge invariant, even though the graph itself isn't?
Oh, I'm not sure I can make that general a statement.
But because
I have to think about it. I have to think about that. I'm making the statement precisely at threshold where I know for sure, because if you're doing atomic physics, you can treat the electron and the muon, the electron and the proton, as standing still. So you're doing the calculation precisely at threshold. I think that makes a difference to what is going on regarding the imaginary contribution coming from the crossed graph.
Oh, okay.
Yeah. I think that matters. I haven't checked up on that lately, but it's important that one of the things that does simplify to a large extent the calculations we have to do is just the comment that I made, that you can treat the electron has a Fermi motion inside the atom, which is not usually called a Fermi motion in this context, of course, but it has a Fermi motion inside the atom. But the scale of that motion is very small compared to anything else in the problem. It's given by alpha times the mass of the electron. Anything else in the problem depends on the mass of the proton or lambda QCD, which are relatively big numbers. And so that Fermi motion is utterly negligible at the level we're calculating now. And so you can set the electron to rest, you can set the proton to rest, and then proceed to calculate.
No. To get a sense of the scale of the problem, could you go back? I think it's graph 24 or 25. You showed the actual data, the actual scattering data.
This is actual data. This is also actual data.
Yes. Well, good. Okay. So you've got a slope of 0.84. What would be the chi-squared if you forced on those data a fit of 0.87?
You get roughly 1% numbers out of this, so you can work it out. 0.87 would be about a 3% discrepancy. So if it's 3% where you would have 1%, that would give you a chi-squared of what? 9 per data point, or 9 for lots of the data points. It's a big chi-squared.
Okay, so yeah. I was just trying to see where the six standard deviations came from. It's really not comparing one result with another, but trying to take these scattering data and forcing on them the other value. That's right. That's the measure of standard deviation.
Well, that is right. Yes, that is right. But you can just also you can calculate the standard deviation for this data by itself, or that data by itself. And again, the point.
I'm sorry. Go ahead.
Oh, I was going to say the 0.88 Fermis is a quotation from the Mainz group itself, and from a number of other people who've done their own analyses of the Mainz data, and it's coming from looking at the whole data set. But they quote a standard deviation on all their coefficients, including the one that gives the proton charge radius. And they're giving you approximately a 1% or somewhat less than 1% uncertainty limit on their number.
Okay. Do they give confidence contours?
Not that I've seen. I'm sure they can, and then maybe some of them have.
Okay.
Yeah. There are correlation contours. I've seen some of those.
Oh, okay.
It's rather crucial. You can imagine an expansion. You have a 1 as your first term in the charge form factor, and then you have a number times q squared and a number times q to the fourth. The number times q squared gives you the slope. The number times q to the fourth gives you the curvature. And I've seen these plots of correlations between the curvature and the slope. You can do funny things there. This data that you're looking at right now, if you still see the data on slide number 25, gives you very little curvature. You can see the curvature on the left-hand picture. There's no visible curvature on the right-hand picture. And if you actually analyze it, you wouldn't see curvature if the q-squared range was small enough anyway. But you can try to do the analysis. The curvature that you get out of that plot on the right-hand side is less than most people would expect. There's a way of saying what you would expect. Well, the curvature, yeah.
Well, I mean, in a sense, that's a measurement of the mean value of r to the 4.
That is right, yes.
But you also have a theoretical expectation for that.
The mean value of r to the 4th should be a couple times the mean value of r squared squared. Would be exactly the same as r squared squared if you had a shell, pure shell, right?
Yeah, okay.
If you have it spread out, you get some number. The question is it bigger than r squared squared, or is it less than r squared squared? The answer is it's bigger than r squared squared by a couple times. You would expect that to be the case. You don't really get that out of this graph.
Yeah,
that people complain about that.
No, that's what I was heading.
Yeah.
Do the measurements in atoms give you the R to the 4 mean value of R to the 4, or just R squared?
No, just R squared.
Okay.
There is sensitivity to everything, of course, if you can make accurate enough measurements. But with the measurements we have, there's no R to the 4th term at any level that we can talk about. And with the scattering data, you can just extend the Q squared up to very large values. Right. Yeah. The atomic people have Q squareds, which are set by the Fermi motion of the electrons. I called it that, just the momentum space wave function of the electrons. That sets their Q squared. And so their Q squared is very small by the standards that you're looking at here. You couldn't measure it in G squared, Jeff squared, or you could measure it in Jeff squared, but you'd have a decimal point and lots of zeros and then a number.
And does that Q squared go up if you go to mu mesic?
No, it doesn't have to.
No, the Fermi motion of the muon. And
I'm sorry. Yes, in the atom. Yes, of course it goes up. It's alpha times the mass of the lepton.
Yes. So
yes,
you get a better. You actually.
You're closer. You're closer to having to worry about it, but you still don't have to worry about it. I've run the numbers. I don't remember the numbers now, but you're still a couple of orders of magnitude away from having to worry about it.
Okay.
Yeah. Whereas with the electron, you're maybe 10 orders of magnitude away or 8 orders of magnitude away from having to worry about it.
No. Any other question?
Yeah, I have a comment against Dombrovsky. So I was just thinking about the lattice calculation because you brought it up and so on. And
to which now?
The lattice calculation.
Oh, very good. Yes.
Of the proton form factor or the radius.
Yes.
The problem is that if you're doing instant form, you have the graphs where the photon makes an extra quark antiquark pair. So you look at the overlaps of the 3 quark wave function with the 5 quark wave function of the proton. And in the front form, we have this miraculous thing. We can choose to frame Q plus equals 0, and then you only get the diagonal box space contributions.
Yeah.
And that's, of course, the famous front form formula. But if you do it in the lattice, you're doing instant form, then you have all the complication. Not only that you're looking at the proton at fixed time rather than instant time rather than front form time, you have the extra graphs of the pairs.
Yep.
So it's going to be very difficult to reconcile a lattice calculation with with anything else because it's instant form. I think in the atomic case, there's no problem because you put in the Feynman diagram basically, so it's already covariant.
Yeah.
But I think the instant form calculation of lattice is really horrendous.
Let me see. I don't do lattice calculations, not counting a little bit of money laundering that we can talk about some other occasion. But I think I would defend them a little bit. They would say everything that you can think of is in there because they don't get a choice about putting things in or leaving things out. They have lattice spacing problems and finite size problems, but all the configurations that you worry about are there. They've got loops in their calculation now.
They have to reconcile how you define electron-proton scattering. I mean, it's really much more difficult. It's not. It's not a physical definition of the form factor. You just take the diagonal matrix elements. So it's got to, I think it's horrendous. But that's just my opinion.
Okay, but they've got 3 quarks coming in and 3 quarks going out. They don't really care as long as the 3 quarks coming in have some overlap with the proton wave function. They manufacture more quark anti-quark pairs on the way in. They're doing a rather complete calculation nowadays.
Yeah. But you have to.
The stuff you're worrying about ought to be there. They start with a matrix element of a current, all right? Sum over charges of Q bar gamma mu Q, etc. So they've got a definition of the current matrix element. It's the same thing we're talking about. And they're not worried about the electrons. They're not worried about the photons. They're just worried about the expression for the current in terms of hadronic fields.
Okay, but does that include the physics of that the photon makes the current makes an extra pair? It's not the current.
Yeah, it should.
Space.
Yeah. Well,
in instant form.
Well, the current is Yeah, the current is diagonal in instant form, but yeah, the current can create a quark-antiquark pair.
Right.
That
And
they've
that-
got that. They have to have that in a modern calculation of the lattice. Yeah.
Okay.
Yeah. For the past 10 years, they've had that stuff. I mean, not 20 years ago, but yeah. I can say more about the lattice calculations, though, since you bring it up, which is that they are very proud. I've only the last paper I've seen is maybe 3-4 years old by now, but they're very proud that they had some results that were within about 2% of the experimental value, or at least what they call the experimental value. But I read the paper, I thought, semi-carefully, and they had 3 different ways of analyzing the data, what they call data. And they got 3 different answers for the proton radius. And it was the radius squared, I think, that differed by 35% from the biggest to the smallest of their 3 different answers. And the uncertainty limits of the 3 different answers made them incompatible with each other. And they picked out the one that was best. And they talked about that. But they were honest in their paper. They showed you the other 2 also. So I'm not sure how well they're doing so far. But they are getting there. They are getting there. The lattice is improving year by year significantly.
Hi, this is Stan Gwazek. I would like to ask if these lattice calculations are not obliged to define what they mean by the contribution of the proton in the sense of radius, because when they calculate with quarks, and they include everything, as you say, including creation of quark-antiquark pairs, and probably including gluons.
Yep.
How do they isolate the property of the proton itself?
They are doing protons in and protons out with different momenta. This is what they're doing so far. There are some techniques that, as far as they know, have not been implemented, where they can actually measure the radius more directly on the lattice. Measure in the sense of a lattice theorist's definition of the word measure. But what they're doing right now, the published stuff, is a proton comes in with one momentum, goes out with a different momentum. So there's a certain q squared. And so then what they are getting as lattice data is something that corresponds to experimental lattice data. It's a matrix element at a certain q squared. And so they have to make measurements at different sets of q squared, and then extrapolate the same way that experimenters have to extrapolate. That's what they're doing right now, at least.
Any other question?
Yes, I have Cédric Orset. Hi, Carl.
Hi there.
Hi. I have a question concerning the extraction of the slope. Because I've been discussing with some colleagues in France working on that, and
Yeah.
telling me that depending whether you include points.
Oh, I'm sorry, I'm not hearing you well. I seem to be hearing every other word or something like that. So
Okay.
Yeah.
Okay. So, having discussed with a colleague in France working on that, can you hear me?
Mm-hmm. Yes.
Okay. He told me that whether you include or not the point at q squared equal to 0, so you set it equal to 1 or not in GE, you may have some difference in the extraction of the slope. So how is it done in the actual analysis and the extraction of the slope?
Yes,
value?
what you say about it making some difference to the slope is absolutely true. And what you do is that you do not set the point at q squared of 0 equal to any value at all. And the reason for doing that is that the normalization, the absolute normalization of these points is not as good as the relative normalization. The absolute normalization is accurate to about 2%. The relative normalization is much better than that. That's the 0.3% number in the cross section I was quoting before. So the relative numbers are good. The absolute numbers are not. And so if it looks like your form factor is going very smoothly into unity, it's because somebody has done the analysis. And after doing the analysis, they do an extrapolation, and then they divide or multiply by whatever number is necessary to make the extrapolation go to 1. When you see this graph, that's been done. They don't
Okay.
assume that the number is 1 at q² of 0.
Okay, thank you.
Yeah.
And the other thing is, if I understood correctly, what you said, it was basically pre-2016. If you just look at the atomic spectroscopy data and electron scattering, you would say that people got the large value. Now,
Yes.
Many of the new experiments, new results point towards a small value. And you said that for the old data, we don't know what went wrong. So what do you think will happen with those data? People would just ignore them at some point, or
I do not know. I just plain do
Okay.
not know. As a remark, though, along these lines, if you are looking at slide number 15, which is what I have up right now, the best data points are not the last one on the bottom, but the 5 just above it. Take those 5 data points just above the very last data point. They all come from the same laboratory. They all come from the LKB, which is part of the University of Paris system. And they're from the year 1990 something, roughly 2000, a little bit before the year 2000. They're all from the same laboratory. And if you and they're very consistent, because if you look back at the other plot, which I'm heading back to now, you notice which is the one point that's definitely in agreement with the larger radius. It is the LKB point, which is about 20 years younger than the other LKB points that I was just commenting about. But the Kostler-Brassel laboratory is very consistent with itself, and it's other people who are getting different values. So I don't know what that speaks to, but
okay.
That,
Thank you.
Yeah, you're welcome. The LKB, incidentally, is redoing their experiment. They have better equipment now than they did in 2018. I've been in touch with them by email, but at the moment, because of the COVID virus, nothing is happening there. But they are hopeful of redoing their experiment with a few dotted I's and crossed T's, etc. And so we shall see what happens.
Well, there's a question in the chat.
Let me see. Somebody will have to read it to me. My chat seems to disappear.
Young Lee is asking, is it possible to obtain the proton radius from the time-like region of the form factor?
I'm hesitating. I would say not really. On the other hand, there are people who do analysis of the data using all the data, which is to say the data, all the space-like q² data, and they try to move their way through the region, the dead region, where there's no possibility of getting experimental data, and then getting into the time-like region. But in the time-like region, you're talking about momentum transfers of 4 proton masses squared at a minimum, different sign. But you are way the heck away from q² of 0, and what they get is a bit of an extra constraint on the slope. And my opinion is that it's not really helping them in any noticeably significant way. Remember, again, if you're in the time-like region, the q² is 4 proton masses squared, and you're interested in the slope of q² of 0, and you're way the heck away from q² of 0. And you can't extrapolate from the time-like region. I'm sorry, that's right. You can't extrapolate from the time-like region down to q² of 0. So my answer is no, but I'm trying to hedge it so that I don't get attacked by some of the people who do these analyses. So, but
other questions?
Stambrowski, let me just come back to one point. Carl, we're going to discuss this later, I know, but
okay.
Go back to the 2-photon correction, to the to all these things, and suppose that the photon has quarks, scalar quarks.
The proton has what?
suppose the proton was made of quarks, just to make things simple. Suppose you had spin zero quarks.
Stan Brodsky, hold on a sec. Carl, when somebody else is speaking, please turn off your mic. Because when somebody talks together with your mic on, we hear the feedback from your mic.
Okay.
And now, Stan, please.
My mic is going off.
All right, Stan, go on.
Yes, so if you do the two photon correction and you have scalar quarks, then you have the famous Siegel operator, the Siegel interaction, the local two photon interaction on the squark. And then I would contend that you cannot use the dispersion analysis to get that real contribution, because it's totally the physics of the two photon correction, the local Siegel interaction involves a different matrix element of the proton. So I don't understand how there's a way to go from the imaginary part to the real part in a legal way, because that two photon contribution, the local interaction on the squarks, is totally separate physics than the rest of it. So it involves different matrix elements of the proton. So this is why I'm challenging the dispersion calculation of the two photon contribution. So I think it's an interesting topic. I mean, maybe I'm wrong, but it seems to me that it's not possible just using gauge invariance and crossing symmetry and so on to actually get that contribution. It's, it does come into the Lorentz theorem, but it's dynamically a different matrix element. It involves 1 over a matrix element proportional to the expectation value of 1 over x. So it's a very different contribution, and it's not given related to the imaginary part of the two photon correction. So I think and it's exactly the same for squarks and quarks. It's just simply you have the z-graph contributions, and they give you the same answer as the local Siegel interaction on the squarks. So I just wanted to add this. I think we'll talk more about it offline maybe, but I think it's an Achilles heel to the two photon correction.
Okay. Oh, this is great. This is great. I think the answer is no, it's not an Achilles heel. I've done these calculations in the sense that both for exercise, I've done scalar protons, but more interestingly,
scalar quarks.
Scalar quarks or protons made out of scalar quarks are done helium-4, which is also very relevant because helium-4 is a spin zero nucleus, and you could talk about the elastic contribution of helium-4. By elastic contribution, I mean the diagram where the thing that goes in between the two photon connections is itself a helium-4. And if you're doing a scalar proton, you're doing scalar quarks, you're doing helium-4, you've got to include this Siegel diagram. And you have to include it for gauge invariance. You have to put it in with a certain form factor, incidentally, in order to make the gauge invariance work, but that's not quite what you're talking about. And then you can either proceed to do the energy contribution calculation in two ways. One is because you've got everything explicit in this case. You can do the calculation directly without dispersion relation. Just proceed, calculate. You include the diagrams that are not the Siegel, and you include the Siegel, which is the point connection diagram. And you get an answer, okay? You get an answer. So you hold that in your head for a little while. And then you say, well, I'm going to check out my dispersive calculation now. What do I have? Well, as you probably remember, there are two form factors for the Compton scattering, whether it's a scalar or a spin-a-half target. This is forward off-shell Compton scattering. There are two form factors or two Compton amplitudes. And that's true whether you have spin zero or spin-a-half. And you have to include the Siegel diagram to get both of those correctly. And the Siegel doesn't give you any imaginary part, as you point out very correctly. And then you write down the dispersion relations, because you have the imaginary parts, and you try to calculate the energy. And one of the things that you realize very quickly is that one of the Compton amplitudes, when you reconstruct it, requires a subtraction. You can't get it without a subtraction, because something that doesn't converge fast enough, you require a subtraction. and then you ask, well, that's good. This is a serious problem in general, but right now it's not such a serious problem in the sense that you have everything explicit. You can say, what is my subtraction term? And you can just look at the whole amplitude because you've got the whole amplitude. You can pick out the subtraction term. And I can tell you what the subtraction term is not maybe in words right now, but on a piece of paper. I'd write it down for you. It comes exactly from the Siegel diagram. In fact, it comes from nothing else but the Siegel diagram as it happens. But nonetheless, it comes from the Siegel diagram. And that's where the Siegel diagram goes in the dispersive calculation. It is there. It is there.
That's exactly right for the case of where you treat the helium-4 as a simple boson. But in the case of the proton, where you have quarks inside, it's a totally different matrix element that comes in. It's because of the compositeness of the proton, and it's really very different. It's not so you cannot use the Lorentz theorem or anything like that comes from just simply Born calculations of the Compton amplitude. It really is a new dynamical contribution, which involves 1/x matrix.
But as I've seen it before. It's right there in the subtraction term. You don't get a choice. And my claim is that what you're worried about is going to go into the subtraction term. It's got to be there.
I am worried about the subtraction term precisely.
Yeah. It's going to be there. The subtraction term is a problem. But one makes the best estimate possible for the subtraction term, and you say, well, maybe you should make a better estimate. But okay. This two-photon correction is there. This fixed pole is there. You don't get a choice about including it or not including it. If it's lingering at very high energies at a fixed q-squared, it's there.
Yep, absolutely right.
And as I say, you don't get a choice about including it or not including it. And the people who do the calculation, therefore, have included it at some level. At least in their minds, they've included it. And whether they have exactly the right form for the subtraction term is a lingering discussion. It's not just in the context of what we're talking about now, but it's a lingering discussion that many people worry about.
Very good. I'm glad you. Okay.
If I can also
have another question, but the last one today.
Okay, if I can also ask a related question to what Stanley just commented on. When I raised the question earlier about a spin-a-half particle, a pure electron, and you do the electron-electron scattering, and you said that there was no discontinuity at threshold, but you had already mentioned there was a subtraction, which I take to mean that when you write the dispersion relation contour integral, the contribution along the circle at infinity is non-zero. Now, and yet the subtracted dispersion relation, then the circle at infinity contribution goes away. So now the question is, if you go to the scalar case and you introduce the Siegel, what does the Siegel do to the circle at infinity? Namely, what happens when the Siegel graph may be real on the real axis, but you've got to continue it into the complex plane. So what happens then?
The Siegel, in this case, is just plain sitting there. The dispersion relation is in the energy. You've got two variables. You've got q-squared and nu. Q-squared is whatever it is. Nu is what I'm calling the energy. The dispersion relation is in the energy, and the Siegel diagram is independent of the energy. It just depends on q-squared. And so you ask, what does it do to the contour at infinity? The answer is, it just sits there. It is there. It's what makes the contour at infinity non-zero. And you get rid of it by dividing by a factor of nu, which is what leads to the subtraction and the dispersion relation. So the answer to your question, I think, is, it's just sitting there. And it messes up the contour at infinity if you don't do a subtraction.
I hope Philip is satisfied with the answer to some extent, at least. Carl, thank you very much for talking today.
Oh, thank you.
Let's thank Carl. And in 2 weeks, on November 25th, we'll have Philip talking about comparison between light front and instant time dynamics. Thank you very much for coming to the seminar. This one is closed now.
Thank you all.
Thanks, Carl. Great talk. Thank you.
Thank you, Carl.
Okay, I'm turning off the recording.